So welcome everybody. My name is Tom van Gerven. I'm the chairman of the working party, the EFCE working party on process intensification. And it's this working party that is organizing together with the EFCE this lecture series or workshop on lifelong learning for process intensification. Before I will give a short introduction to the working party and its activities, I would like to give the floor to the EFCE representative, David Bogle. David, you have the floor. Thank you, Tom.
So it's a great pleasure to be here. My name is David Bogle. I'm the scientific vice president of the European Federation of Chemical Engineers, and I'm a professor of chemical engineering at University College London. What we're doing with the EFC is we have this series of virtuals, what we're calling spotlight talks, actually, on significant topics in chemical engineering. And 11 of our working parties, 11 of our technical groups, either working parties or sections, are delivering short sessions, 3 or 4 talks by leading industrial and academic experts. We've got 11 of them. Chemical reaction engineering, education, energy, loss prevention and safety promotion, mechanics of particulate solids, mixing, multi-phase flow, process intensification today, quality by design, static electricity in industry, and thermodynamics and transport properties. And each session will focus on key topics in the area. And the idea is we're towards the end of them. I think there's 3 more to go. The idea is that people can sample, they go to the ones of most interest, but also potentially sample across the different areas to encourage cross-fertilization between the specialist areas in chemical engineering. So the EFC promotes scientific collaboration and supports the work of chemical engineers and collaborating professionals in 30 European countries, representing more than 100,000 chemical engineers in Europe. With its working parties and sections, it covers all areas of chemical engineering. The EFC's working parties and sections are right at the core of the organization, and they form the scientific engine that drives many of the EFC's activities. And each of our working parties and sections focus on a specific aspect, and they maintain the important forum for networking among chemical engineers in Europe across academia and industry, and indeed beyond. So thanks very much. Just a few thanks. Thanks very much to Maarten, who the scientific secretary of the EFC, and to Ines Hondorf from the EFC in Frankfurt for all the organizing of all these activities. There's really a lot of hard work in setting up. And thanks very much to the process intensification work, to Tom and the others for putting this one on for us. Thank you.
Thank you very much, David, for the introduction. So I hope you now can all see my screen. So yes, this is the lifelong learning of process intensification for an innovative industry spotlight series. So this is the program. You've seen it before. We start with an introduction. David has already represented EFCE or informed us about EFCE. I will give a short presentation about the working party, and then we have 3 lectures on different angles, I would say, of lifelong learning. Professor David Rivas from Twente University will give us a review on how process intensification is being educated at university level. Jan Harmsen and Professor Maarten Verkerk will give us an insight on how process intensification training could help industry to perform or to develop better processes. And then we have, as the last lecture, an example of how process intensification changes industry. Wim Dermaut from Agfa Gevaert will present a new development in his company with an intensified process by means of flow technology. So let me start by introducing to you a little bit more on the Working Party of Process Intensification. As David said, it's one of the many working parties at the core of the EFCE. And the Working Party in Process Intensification exists since 2005. So we're more or less in our 15th year. The typical composition of working parties is that there's one delegate from industry and one delegate from academia per country, per European country. There's some flexibility by having invited partners or invited delegates, but this is a typical composition type where we try to have both industry and academia represented per country. If you're interested in more information about the Working Party, I've noted here the website or the web page of the Working Party, which is under the umbrella of the EFCE website. So if you look at the mission of the Working Party, in a nutshell, basically it is spreading the news and spreading knowledge on process intensification. And I've highlighted in blue here some of the aspects of the mission that are particularly relevant for this specific spotlight talk. We try to look at how we can get process intensification into training at the universities. We try to participate in education, dissemination, exchange of knowledge, and we also support the production of textbooks and other publications. And you will see in the next lectures that each of the presenters has contributed to one or more of these aspects of the mission. What I want to do in my introduction is just shortly highlight three activities of the PI Working Party and even broader the PI community. First of all, the conference series that we have, the awards that we're handing out, and the support we give to handbooks and papers on process intensification. We have a conference series, the International Process Intensification Conference. This has actually grown out of the European Process Intensification Conference, which was called EPIC. But since two editions, we have converted this into an international one with a lot of contributions from the US, from North America, South America, but also Asia. So the last one took place in 2019, last year. We had about 160 participants. If you look at the pie diagrams on the right-hand side, it shows that we had about 70% representatives from academia, 30% from industry, which is not bad. It's kind of quite a good balance. Obviously, being held in Europe, we had as a majority people from Europe, but also quite a significant contribution or participation by people from Asia and America. Typically after the conference, we have special issues, and this time we had special issues in two academic or two scientific journals, the Chemical Engineering and Processing Journal and the more new Journal of Advanced Manufacturing and Processing. And I can already announce that IPIC 3, which would normally have been organized in 2021, but due to obvious reasons, we decided to postpone it for 1 year, and this will take place in May 2022, and this will take place in Beijing. So we're really going international, and we're looking forward to everybody that's interested in process intensification to see you in Beijing in 2022. Regarding the awards, we have two awards that we award every 2 years. The first one is the EFCE Excellence Awards in Process Intensification for actually the best or the most outstanding PhD thesis in the domain of process intensification. As you can see, the last one, 2019, has been awarded to Andy and Zara from Greece, who is now working in the US. You see here a picture of Andy on the right-hand side receiving his award. The second award is, as the first award is more dedicated toward towards science. The second award is dedicated towards industry. And so this award is highlighting a novel development, a novel industrial innovation in industry related to process intensification. And the last winner of this award has been Agfa Gevaert, and that's why we also invited Wim Dermaut to give a presentation in this lecture series. And this is a nice picture of Wim and his colleague receiving the award. So again, the presentation of Wim is at the end of the morning session where he will talk about how they implemented intensification or process intensification in their company. And then a third activity of the PI community or the PI working party is to also support and develop handbooks and papers. I've just listed a couple of them. Of course, it's always difficult to be very exhaustive on this. But just as a couple of them, we have the Fundamentals of Process Intensification, which has come out, I guess, 2019. We have process intensification for design, industrial innovation practices and education. This is the book by Jan Harmsen and Maarten Verkerk, of which they will take inspiration for the lecture, for their lecture later this morning. There's also the handbook on process integration and intensification by Jiri Klemes, who will get, or which will get, a third edition coming out soon, probably 2021. I also want to highlight the fact that not only handbooks are being supported, but also papers. And I really want to highlight the activity that David Rivas and also Daria Bofito did in last year to come up with these two papers on the current education of process intensification, and David will talk about this in his lecture as well. And obviously, besides papers and handbooks, there's also a lot of journals that are related to process intensification. The Chemical Engineering and Processing journal, which I already mentioned, the newer one, Journal of Advanced Manufacturing and Processing, since 2019, and then there's even a more recent one, Open Access Frontiers in Chemical Engineering, for the section of Microfluidic Engineering and Process Intensification. This concludes my introduction. So this is a program, and I'll stop sharing my screen to see whether there's at this moment any questions, but if there's not, there's one question here. Are you going to share the presentations after this spotlight talk? So the idea is indeed that this whole presentation is being recorded, and the recordings will be made available for the public, so they will be posted on the EFCE website. Okay, then I hand the floor to David Rivas. David, you have the floor for your presentation.
Okay, thanks Tom for such a nice introduction. Can you all hear me properly and see my screen? All right, I think I should move this one to the other side. Okay, well, I would like to start by welcoming you all to this talk. I'm very thankful for having the chance to show you about our efforts to try to explain how we achieved these two papers that Tom shortly introduced. And I will also take the chance to tell you a bit more about our activities here at the University of Twente. So I'm an associate professor at the Mesa Plus Institute, and I work mostly in microfluidics, but I've been teaching process intensification for about 5 years now. And I've been also a secretary from the Process Intensification Network in the Netherlands. And well, without distracting you more, I want to actually share a bit of a retrospective story, because obviously, as Tom just said, we had these two nice papers which have approximately 30 co-authors in each of them. And well, I was asked to give you a bit of a, let's say, a summary of this feat, let's say. I think it's a great achievement to get the opinion of so many experts on paper. And well, it happened actually a year in June 2019, still last year. It feels very far away. But this is a unique location. So for many of you listening that are interested in having a unique venue to bring together experts from different fields, I strongly recommend it. So we actually had the support from, well, the Dutch Organization for Scientific Research, University of Leiden, and well, the presence of not only scientists and let's say professors from the academy on the spot, but we also had yeah, companies and people who are not connected directly to universities. For example, Jan was also there, and his input was very helpful, such as Tom managed to join us after the IPIC conference in Belgium. So some of the big questions that we all have when we're trying to teach the new generations of engineers, and interestingly, they also have similar questions. It's like, so what do we really need to teach the engineer of the future? How can we contribute to a sustainable future? Are we already prepared with the sufficient tools to do that? Is there a new reactor that we could use to replace existing reactors? Other questions in that is like, okay, is the university the right place to learn it? No? Like, how can we make sure, as we are talking today about lifelong learning, that people who maybe left the university 10, 20 years ago get the best information out there? Well, and then some question that is emerging more and more in the universities is like, can I become my own boss? No? Because students follow in the news that many big companies sometimes are shedding off labs or yeah, firing researchers. So this is something that we need to also try to educate the new engineers, that at some point they can also have their own company, be their own bosses. Now, a very short detour connected to this entrepreneurial or valorization approach. For those of you who are not familiar with the University of Twente, well, we're trying to claim that we are the most entrepreneurial university in Europe, at least. And there are several examples of success stories. So some of you probably have used Booking or Takeaway. Here is a small logo of the spin-off company that I started about 7 years ago. And well, for those who are interested in knowing more about Twente, here's some website. As I mentioned in my first slide, I'm embedded in the mesoscale chemical systems. The first work, this mesoscale, gives us a lot of freedom to move from the nano, micro, and all until the scale that we decide is large enough to do our research. And well, we are a multidisciplinary group with sufficient, let's say, clean room technicians. So we do a lot of microfabrication ourselves. And well, my vision, which I would not be talking much about today, so my own research is about exploiting bubbles and well, doing applicable research. Basically, what I'm trying to say with this is that I'm working on problems that could be used by society in the shortest time possible. Now, going back to the original story, we wrote a proposal for the Lawrence Center to, that allowed us to have for 1 week about 30 experts, as I said. And this is what initially we thought we would do. So we had some participants, some potential participants, and then new additions came in time. And we thought, well, we wanted to write one paper, as you say here in the output number 4. And it turned out that we generated so much information that one was not enough. So that's how we split it into 2. And I will tell you the highlights of both papers in the upcoming slides. Now, how it worked, so we had every morning a structure like this. So there will be 1 or 2 or 3 top inspirational lectures. So actually, we requested the speakers not to tell us the usual story of what they do in their lab, but actually we gave them some sort of burning questions or some topic that would be the starting point to debate in the classroom. You will see the classroom we had. And then in the afternoon, we will split into smaller groups to discuss some of the elements connected to those lectures given in the morning. So you can see here a feeling. So actually it felt like a classroom. So we had people who probably didn't sit in a classroom for like 30 years going to the blackboard and well, giving input. So at the end of each day, we will collect all this information and try to give the next morning some summary in plenary session so that everybody could follow the whole thinking process. Now, probably it's important to define what we mean with process intensification. And in these two papers, we have updated or refined the definition, which of course there are many books out there, but we try to synthesize it with the opinion of these 30 experts that joined during that week. So the most interesting part is that we see that PI can really help the chemical industry to jump from the fossil-based, say, track record or history path that we've been working for many years now, and move into some renewable-based chemistry. And we identified these 6 sustainable goals from the United Nations. And well, in view of time and also to give chance for more questions, I'm going to skip some of these slides or move a bit faster so that we can have a better dialogue. And most of the details you anyway can see in the paper. I have to say the second part is open source, so you can download it freely. If you, for some reason, have no access to part 1, there are 2 ways to get it. It's either through my university website, so we have it already posted there, I think also on ResearchGate, but also you can send me an email and I'm more than happy to share with you. Now, an interesting update that we bring to the PI definition is that we all agreed that the I in PI could be seen as innovation, improvement, and we also thought that it would be important for newcomers to the field to at least check this framework given by the structure, energy, synergy, time approaches, and the 4 principles of PI that were introduced a while ago by Tom and Andrzej Stankiewicz. And well, it's not my role to walk you through this schematic. So this is an invitation for some of you who are not familiar with these schematics. Please take a look at it because it's very helpful. Now, after that event, we also kept thinking. So Daria, my co-applicant for the event in the Leuven Center, and we had another publication that goes a bit more into details and it's a bit more technical because the part 1 and part 2 papers that we're discussing right now are a bit more on the educational challenges and some opportunities, and you will see some examples of what was discussed there. But for some of you that would like to have a recent snapshot on how PI can connect the different scales and somehow the relation with process system engineering, please check this paper as well. Now, going back to the definitions of PI, so we also agreed that we see it as some sort of departure from the conventional way of doing things. We also identified that PI should in the future be not only concerned about the equipment or the specific driver or that puts you in that in the first place, but it's like what really happens outside the process and what are the consequences that your process could have for the environment or the economy. So instead of having unit operations, we will have some, how to say, like functions, and that can be a bit difficult to explain here, but well, it's better detailed in the paper. And one element that process intensification typically brings is combining several concepts or equipment or processes into one, and ideally you should have some significant improvement by doing so. And well, of course, this new technology or the intensified process or reactor in principle will be more efficient and well, environmentally friendly, etc. So the main conclusion of part 1 is that, well, when you look at the toolbox that a chemical engineer typically has, so PI brings a lot of new tools to combine with the existing set of tools that traditionally we've been learning over the years. So here I'm using a graphic from the Rapid Institute, so most of you probably are familiar with their activities there. But I think the most important take-home message is that obviously we all sitting there knew that this is important, but to really inform the public and the politicians, because we had a few representatives from governmental institutions, is that we all think that the work of the academia together with industry is the most important one. And well, this can help us accelerate the penetration of PI in the work floor, because if the engineers studying now in our universities have a clearer understanding of what is possible with PI, then it's a lot easier to bring it to, let's say, existing companies or even creating new companies. Well, also we are having say an open chest saying like, indeed, not all processes need to be intensified, so we have to be self-critical and well, transparent. And well, we also think that since we were talking also about education, some of the elements we discussed in that paper, if you replace, let's say, chemical engineering from the pedagogical point of view, you could also apply to other disciplines. Well, this is the main message from part 1. Now, part 2, we went a bit more into the educational tools, or like what has worked for us until now, so that if somebody in the future would like to start a new course, could start already from something that has been proven, and you don't have to reinvent the wheel. So we brought up this interesting graphic. I'll try to explain it for you. So for those of you who have heard about educational processes, the most accepted, say, framework right now has to do with these levels of cognitive skills. So there's a lower level where you just typically have to remember and understand. So these are the lower levels, but then you move on into this, how to say, pyramid in this case, or triangle, and you achieve a higher level when you are able to create or evaluate things that are not even existing. So this is very important because we see that PI adds a lot of integration for educating chemicals engineers for the future. So of course you always have the traditional knowledge that needs to be there, but this is, let's say, the traditional way of looking at chemical engineering until, I don't know, 20, 30 years ago. And now many universities are focusing more on this teamwork and, well, creating, ideating, and designing things that do not exist. And PI really brings a unique opportunity because there are many new stuff that have not even been tested in large-scale chemical plants. Now, we also try to highlight the difference between problem-based learning and challenge-based learning. So problem-based learning is a bit lower in this sort of pyramid that we were just discussing. And well, we all agreed that in the universities that we've been teaching PI, in any, let's say, level, could be bachelor or master's, typically is being taught more at the master's level. Challenge-based learning seems to be the most suitable, and because it really allows the student to go through the whole pyramid that we just discussed. Then, well, the main conclusions for part 2 is that we need to really educate not only at the master's level, the earliest we can, the better, but we also need to look for the postgraduate education. Some universities are obviously giving the opportunity to professionals to come back and take a few selected courses. So if we manage to offer some sort of courses, let's say, to refresh your knowledge, and people from industry could come and take those lectures, that would be very useful. I myself had 2 students a couple of years ago that left the university like 20 years ago. So they took particularly the process intensification principles course because they wanted to see what was out there, and just by the description of the course, it was interesting enough for them. Well, of course, we all agree that PI has some risks in the technological and investment side. No need to discuss this right now. But the most important message for all of you that are connected to companies is that we really need input from what is working for the industry, because the students feel very motivated to work in problems that are reality, like are really happening now, not in a book that was written 5 years ago, but sometimes what we organize is type of problem-based learning or challenge-based learning that the company sees in the final presentation of the project, so that they can really give a measure, oh, what you're saying makes sense, or what you're saying, well, would never fly because it's I don't know, commercially impossible. But that really gives an interesting motivation for the student. And well, this is more or less what I was mentioning. The more case studies we have to show that PI works, the better the students will be convinced, and they become ambassadors themselves when they join the workforce. And well, this I mentioned it already. It's important to teach them the PI because, as I said, either they join an existing company, but they could also start their own company. The appendices, actually, I wanted to have, it would be probably too long of a paper, but the most useful tools for many of you might be to actually check the appendices, because we have a lot of interesting tables describing what has been taught in the past decades even. So each university providing the number of the teachers, the credits, how many editions, and some descriptions about each course. So I highly recommend to check that. And then we also have examples of activities or some exercises that we are giving the students from all these universities. We have links, we have, let's say, well-described assignments, so you could even use them on your own because they're already open access. But if you want to contact the teacher and improve something, then everybody's more than happy to receive emails. One interesting thing that was discussed during the meeting in that week is also like, how can we teach the students the superiority of PI? And here I'm using a slide that you could see as a joke, and partly it's a joke, but it's actually a serious attempt that together with some co-authors we brought to the field, and it's actually being used nowadays by some PI experts. And here what I want to illustrate with this image is that it's sometimes very difficult to define which is the best precedent. Of course, you could extrapolate to PI, like which is the best technology. If you look only at the height, that is kind of easy, but you could look into different categories. And that makes it very difficult at some point for plant engineers or students to decide, hey, how I can be convinced that this spinning this reactor or this steel column reactor is better than what has been in use for more than 40 years. So I'm not going to give you all the details because we have like 30 more minutes to finish and also for the question. But all this is described in this paper, and some examples are given in these two papers that I'm discussing with you today. Just to give you an example, sometimes when you have to compare between more than one alternative, so if you have a batch process or continuous batch or a hybrid, then this method is quite a simple starting point. Even for the students, it's very illustrative, but it's also being used in industry. I'll give you one example in the next slide. But to make a long story short, you can have several factors or drivers or whatever you want and put them in this very simple table, and you come up with a number. And if the number is larger than 1, then the new technology or the new reactor is better in principle than the one that you were comparing it against. Well, some of the advantages is that you can actually put together many of these factors and forget about the units, because of course you cannot really compare money with pressure and other stuff, at least at a first sight. And well, you end up having this sort of a number that is non-dimensional. So this has been used in practice. For example, this is a water utility company here in the Netherlands, and they were planning to replace their process lines by reverse osmosis plant. And so we did this analysis together, and well, it turned out that based at least in these 3 factors, sometimes it's difficult to bring enough factors to have an interesting case. But in this paper, you can find many more elaborated cases about this. More recently, the same method was used in more academic settings, but then using ultrasound, which is a process intensification technique in itself, and for advanced oxidation processes. And then again here, you have 3 factors. So the cost of the catalyst, the reaction rate, the concentration of hydroterephthalic acid. And then in the end, you have a value that if it's larger than 1, then by using this improved intensified reactor, then you have a better result than with a conventional advanced oxidation process. If this kind of resonates with you, we have a LinkedIn group about this calculation of this method. So I would be happy to see you there. And with this, I would like to thank the organizers again for giving me this chance to talk to you. Thank you for listening, and I'm open for any questions you might have.
Okay, thank you very much, David, for this interesting talk. We indeed have a couple of questions. I see that Pascal PTO has a question about additive manufacturing and 3D printing. Do you believe that is interesting to add to the education program, perhaps as part of PI? He says that he's currently doing that in France, and he concludes that it's often a differentiating item for students. So what is your opinion, David?
Well, I think definitely yes. Any technology or tool out there that can help us give the students the chance to test their abilities should be used. I mean, what I understand from 3D printing and how I use it with my PhD students mostly is that you have an idea, you don't need to really wait until somebody in the workshop does it for you. So you can actually design, make your drawing, submit to the machine, and next morning sometimes you have already what you produced. And then you can iterate, because if it doesn't work, then the next day you have a new version. So I think this chance that 3D printing can give us is unique. So I would support any initiative in that direction.
Mm-hmm. Okay. Yvonne van Delft is asking, are companies interested in PI, and what opportunities are there for R&D on PI? This is perhaps a bit beyond your presentation, but maybe you want to share some thoughts.
Yeah, so I think typically companies might be doing PI secretly, either knowing what PI means or unaware of what it is. So I can tell from my own experience, and that's how I got to know Tom when I visited him the first time. Some people are doing already elements of PI intuitively. So of course, if a company doesn't see a big benefit on changing a process or a production line or a reactor, they will not do it. I mean, they don't have time to really look at the academic papers and enthusiastic researchers or optimistic innovators. So probably Jan can tell more about that, or people who are more connected to the work floor of companies. But that's why I brought up precisely this method to compare, because sometimes what we are missing is a clear message like, okay, this technology is much better, not because it's better for the environment, not because, so there are many factors that you need to convince, and most of the times it's only cost. If it's just more expensive, probably many companies will not be able to afford the change. But it's, I think, a very valid question, and we all need to work together to make PI an appealing alternative for any company out there.
Okay, thank you. And I agree that Jan and perhaps Wim Dermaut later on can also come back to this question about the company interests. So to the audience, if you have further questions, you can either post them in the Q&A or in the chat, and then I will pick or select a couple of them. I have one more question, David, for you. Question that is sometimes arises if you look at people in the curriculum development in universities is, should PI be a individual course or a separate course? Shouldn't it be, as you mentioned yourself, process design exercises together with companies? Shouldn't it be, for example, included in existing courses like chemical reaction engineering, separation processes, and many others? What would be your opinion about that?
Well, I think the easiest is to piggyback on existing courses, because if you're really starting from scratch, more or less like I had to do back in 2014, it takes a lot of energy and effort to pull together material and bring something new that is not already given in a different university. And then with time, you can see whether there's a demand or if students are interested in an isolated or standalone course. Because what I feel is that already the students are overwhelmed by the amount of choices they have right now to study. Many universities have way more optional courses that you could actually study in a lifetime. So I think we will add to the confusion to create one course separately, which will be having divided attention from students. So I think it's smarter to probably get the most popular course in your faculty, talk to the instructor or the teacher or whatever, and try to see how you could bring one or two examples so that we teach the students something without they knowing that they're actually getting the PI, at least at the beginning. And later on you reveal, well, actually the tools you've been using and all these, let's say the approaches or the principles are already, I'd say, a framework and has been defined as process intensification. And you have a long list of a book or articles you can look into it. But I think the students have either 4 years in the bachelor or master's, 2 years to accumulate or acquire a lot of knowledge. And we would be more effective if we just plant a small seed as, let's say, one assignment or one end project as part of a course, ideally a mandatory course that so that most students will see it. So you have higher chances than just creating one standalone. That would be my main advice.
Okay, okay. I have one more question. I see that there's no other questions being posted in the chat or the Q&A for the moment. So I have one concluding question. You raised the point of metrics and you suggested this intensification factor. It's a bit like LCA where you have different possibilities to measure something and then you try to come up with one single number at the end. But how do you weigh different perspectives, costs, energy consumption? How do you do that? Should we do that, or should we just sum them up?
So the way that this method was designed was to allow the opportunity for those who already have enough experience or knowledge on a topic to assign different weights to the different factors. So the way it starts is we have this exponent, which is assigned the value 1 or -1, whether you want the factor to decrease or increase. If you have a group of experts and decide unanimously, ideally, that safety is more important than, I don't know, yield or efficiency, then you can alter this D value. And that the nicest thing is that it's very transparent and very simple. So when you compare it to other methods, when you try to inform, I don't know, management or people who have maybe little background on the specific topic, this is such a simple table that you can agree, okay, so I see here that you are dividing these two values and this exponent, which is 1 or different than 1 is the message, whether you want it or not, and how important it is. So it's there. And if any of you guys listening want to discuss more about it, I'm more than happy to have a team chat or a video call to go further.
Okay, super. Well, there's one more question. Huub van Grieken is asking, I'm an old, and this will be really the last one before the break. I'm an old-fashioned chemical engineer, graduated in 1987, new to PI. Where should I start to gain more insight in this field?
So my advice would be looking at this paper that you, Tom, published a few years ago, because I'm very visual, or many engineers are trained in a way that we see things clearly when you see graphics and arrows and things like that. So I would start there in the sense that it gives you some sort of higher level visual, let's say, set of tools or angles to look at a given problem. So instead of looking at a long list of reactors out there that have been demonstrated to be good for PI, starting from some of this either review or this or maybe the first chapter of some of the different books that Tom presented at the beginning, I will start there, because the literature right now on research papers is huge. And yeah, it takes a lot of time, and only if you're interested in one particular type of technology, I don't know, plasma or ultrasound or spinning this reactor, then you can narrow it down and really focus there. But to get a starting point, I would suggest actually part 1 and part 2, or at least part 1 gives already a good starting point of the papers we discussed today.
Okay, super. Thank you very much, David.
You're welcome. Thanks, and well, let's enjoy the rest of the lectures.
Yes. So looking at the program, we have, it's 11:20 now, we have a 10 minutes break.
Okay, Tom, thanks for the introduction. So our focus will be in this short half hour on training for industry. So we only skim over the information about process intensification. The first part, which I will do, is about process design. And I'll first start with the 2 approaches to design, which you can find in the literature. And then I'll present my own view, which is a merging of the 2 approaches. And then we'll go into the innovation practices, and then Maarten will take that part into, and then Maarten will finish with how a training for industry course could look like. So I'll start with the PI approaches. Ines, next slide, please. Simply stated, how to start with process intensification, my answer would be start with buying this book, The Fundamentals of Process Intensification, because that simply puts the whole approach, the research approach to process intensification. The book explains how you could do research on new process intensifications, and you can do the research using their principles. And the principles are very nicely stated, I think. The principles are maximize molecular events, which means that you try to maximize the reaction you want, both inside the molecule and between the molecules. They call that maximize molecular events, and they have lots and lots of tricks of maximizing molecular events. The second thing is that each molecule should have the same experience, so you have exactly the same product and you make one product only. The third one is very interesting. It's about optimizing, and it's optimizing for driving forces and specific surface areas. You cannot have a very high driving force and little surface area, then still the equipment will be very large. You can have an enormous surface area created, for instance, by having a very intense mixing and a low driving force, but then the energy required for creating the surface areas are also very high. So you have to optimize for both. And the book describes how you can do that using all kinds of methods. And then the 4th bullet point is look for synergy between the effects you're looking at. So maximize synergistic effects of partial processes. Those are the principles, and the book is 400 pages, so I cannot go into any detail, but that's the thing about the principles. Then secondly, the book is about domains, which has more to do with the technologies or the techniques. The first domain they discuss is spatial. For instance, if you use structured packing for creating surface area, then that's part of the spatial domain. Then the second domain is thermodynamic. It's the way you either supply energy or extract energy from the process you're interested in. So for instance, if you microwave applications, that's part of the thermodynamic domain. Then the function synergy, that's about finding ways of combining interesting functions like a separation and a reaction, for instance. So you have a reactive separation. The temporal operation is a dynamic operation. So very cleverly, you can dynamically operate a process and have advantages of just using a dynamic operation. The book not only discusses the principles and the domains, it also gives a very long list with pictures and short descriptions of already established new process intensified technologies. And then process designers can take that list and select the interesting one and do their own process design. So here you have a approach, which I call the research approach, because it goes via research to establish new process intensifications, and the process designer can take these new ones as established building blocks or established new process unit operations. Next slide, please. The other approach, also described in literature, is about process intensification as a design or a process synthesis approach. Here, the focus is on designing, not using unit operations, but using functions. So you first, in the scoping, you define the problem, inputs and outputs, and lots of other criteria, of course. And then you generate lots of ideas, but using the function description. The function is simply stated what should be done, not how it should be done. And functions are quickly pictured or can be drawn quickly because you only have to state what you want to achieve in that step. And then once you define the functions, then you can try to integrate the functions, and integrating the functions, of course, is not so easy. And there you use modeling and simulation to see whether the integrated idea is feasible. And also later, when you have followed a few cycles of synthesis and analysis, you can optimize the new idea. And once you're happy enough, you can send it to the evaluation and go to the next innovation step. The founding father, so to say, of this method is Jeff Ciarola. He got his PhD in 1971 on this process synthesis method. And he is also the founding father of the Eastman chemical reactive distillation, where you can see all the ideas into a single clever column, which has been commercialized. And I also found a book, there are several more, on process synthesis and process intensification, where you can see the methods to use this new way of designing. Maybe I should stress, it's not one or the other, and maybe I'll try to explain that in the next slides. Next slide, please. Next slide, I've tried to combine the two methods in a single method. So I use the domain things of Tom van Gerven, and I put them in a sequence. It's still okay? People can still hear me? Okay. The first step is consider the whole process, which I call plant-wide. So you look at input to output and what should be done to get from input to output. And of course, it's very advantageous if your reaction doesn't produce any byproducts. So you can use here all the tricks in the book of Tom van Gerven and Stankiewicz of not having byproducts. The second step is functions and their integration. So try to minimize the process equipment you have, because any process you have and you can minimize them, you have less flanges, less connections, less control. Also, if you look at the thermodynamics, you're far more efficient. So you both gain on capital cost and you also gain on energy requirements. And a beautiful example is, of course, reactive distillation. The third one is a dynamic trick. And there is an enormous number of commercial scale dynamic operations, which they call reverse flow combustors, where they cleverly use the dynamic trick, the temporal trick, for having a beautiful solution. And another simple one is cyclic distillation, which also very cleverly uses, on the one hand, the process is continuous, but because they use this cycle of feed, which have periods, that it behaves like a batch reactor. So in one part of the cycle, the liquid is the main phase, and in the next cycle, the gas is the main phase, but in between you have nearly a batch process. So you have very good residence time, narrow residence time distributions. The fourth is the thermodynamic. Consider alternative ways of supplying the energy to your process. That could be microwaves, that could be other ways. And then number 5, that's the equipment. can you find, there's a beautiful list of types of equipment for all kinds of contacting. Can you select a piece of equipment which is really the best for your problem in process design? And one of the questions industry also asked, can we use this for revamping an existing process? And the answer is yes, especially process intensification, because it requires a smaller area. You can often do that in an existing process. And also the first reactor distillation in Shell was a revamp of an existing distillation where they put catalyst bags on the trays to have the reaction. So revamps are certainly an option in process intensification. Next slide, please. And here's the example which we use in our book a lot. It's a commercial scale process developed by BTG BTL in Twente. The biomass is first dried, then the second step is a novel fluid bed rotating cone reactor where you quickly and rapidly mix hot sand with the biomass. The biomass gasifies very rapidly. The hot sand and the vapor goes into a separator. The sand plus the coke goes to a fluid bed combustor where you combust and the coke, so you have the hot sand that is recycled back to the reactor. And then the second thing is this, you have the vapor flow and you condense the vapor and then finally have your liquid oil. Beautiful process, and I will show, next slide please. Here you see the process intensification elements. The first trick is they don't use any fluidization gas. They only use the biomass which is gasified as the fluidization gas. And not having an additional gas, of course, helps enormously downstream. The separation is far more easy. Also the mixing, everybody knows in pyrolysis you need very rapid heat up and very rapid cool down. Very rapid heat up with nearly a plug flow of your vapor also helps to have a high yield. And the energy is also alternative here. You don't have an heat exchanger here, but you use the hot sand to supply the heat. The next thing where they have used process intensification is in the spray condenser. You have the cooled product oil, and part of that you recycle back to the spray tower, and there the cooled droplets condense the biogas, and then you have the final oil. So you have a very nice cooling and separation without any heat exchanger. And I think, next slide, please. Oh yes, here's the result. The first plant was built in 2015. The second one is now starting up in Finland. It's a reasonably high, for biomass conversion, reasonably a large scale process for if you compare it to crude oil, it is of course a very small process, but they cleverly made it into a modules, and the modules are tested first dry in the Netherlands and then transported by truck to Finland, and there they are assembled, and then the startup can start. Next slide, please. And I now give the floor to Maarten. Maarten, hit the road, I would say.
Jan, thank you very much. I hope everybody can hear me well. I would like to start to make a small confession in that way. When I look back to my career, it is a mixture of hard factors and soft skills. My first PhD was in solid state chemistry, and after that I did research at Royal Philips, and I was for more than 15 years operation manager and R&D manager in ceramics industry, ceramics process industry, and glass industry. And in 2004, I wrote a second PhD, and that was about processes on the shop floor in factories. And finally, it was about power and trust. And later on, I became a professor in philosophy and ethics of technology. So if you see in my career, there are a lot of hard factors and a lot of soft skills. And I had an intensive dialogue with Jan about hard methods and soft skills with respect to process intensification. And I would like to share some thoughts about it. And we call that the innovation practices methods. And we would like to present you three important items. First, the FIP model. Second, the idea of innovation practices with respect to a multidisciplinary team approach. And lastly, about innovation practices, a cooperation in innovation networks. Next slide, please, Ines. The starting point of the FIP model, and FIP is about values, interests, and beliefs. The starting point is the practice of engineers. We start with what engineers are doing and saying. And we use for that the word practice. Yes, so it is not about management. It is not about theoretical models or I don't know what. No, the practice model starts with what engineers do and say. And this practice model I've developed in close cooperation with engineers from different disciplines. And when I developed it further with Jan, we changed it a bit so that it also fits very well to the process industry. So the key elements of this model are three soft parts. That is values of engineers, interests of stakeholders, and beliefs in society. And I will explain that further. Next sheet, please. Now I will go back to the innovation practice of BTG, BTL. Why was this group, this company so successful? Was it only because they had the right process engineer approach, the process intensification approach, or is there more? We did a lot of interviews with the founders of this group. And we found that it is not only about hard factors, but that soft factors also play an important role. First, let's look at the values. When we interviewed these engineers, we found out that there were two values very dominant. All the engineers, they wanted to be innovative. And all the engineers, they wanted to develop a commercial scale operation. And these two values guided their action, guided their words, guided all their interactions also with the environments. The second point is the interest of stakeholders. There were a lot of local stakeholders involved in BTG, BTGL. And they had one common interest, that was to generate employability for the region. And also that common interest, the great influence, large influence on this project. And finally, there was a belief that was shared by all stakeholders, and especially also by the authorities, to realize process intensification, to realize this type of innovation, you need local cooperation. Next sheet, please. I would like to come to the second point. As I told you, I have a broad experience in industry within Philips and also about innovation. And in generally, you can say there are three main practices in the industry. The first is research and development. Second, marketing and sales. And the third one is operations. If you look to these three practices from the practice point of view, then you realize that every practice has its own culture, own language, unique knowledge, specific contribution to innovation. often we think that the real contribution to innovation is by R&D. I think R&D is tremendous important, but also marketing and sales and operation can have a very valuable contribution to innovation. And Jan and I, we talk about innovation practices, and that implies for us an intense cooperation of R&D, M&S, and operations. All have to contribute to innovation. And if we look back to BTG, BTL, and the same holds for all the other cases we describe in our book, there was one innovation practice. There were no walls between R&D, M&S, and OPS. All these innovation practices were working together, and all their specific knowledge was used for the development of PI. Next sheet, please, Ines. The third point I would like to focus on is the idea of innovation networks. We see that with all cases described in our book, it is not only about one single company with one single innovation. It's always a cooperation of industries, universities, customers, EPC contractors, authorities, and so on. And here, basically the same holds. If you look to all these stakeholders, to all these partners, they have an own culture, an own language, a unique knowledge, and they all can deliver a specific contribution to innovation. And that means that we learned from the case studies in our book that if you really want to have a good process intensification, then you need an innovation network. You need an ecosystem. And especially we saw that in BTG BTL. BTG BTL is located in the eastern parts of the Netherlands. And I have lived there for many years. Now I live in the south of the Netherlands. And to be honest, it are two different cultures, although it is in the same culture. But we don't speak really the same language. And what we saw in this example, BTG BTL, it was a local network based on trust. And every party in that network was one of us. Yes. Next slide, please. So if you here, you see on the left side, the history of this process in innovation. You see on the other axis, you see the different parties. It started in the 80s. And you see that at the moment that BTG BTL was founded, it was all founded by engineers, delivered, to say it in that way, by the Twente University. And at the moment when the network spread out and the innovation network was established with the plant, the customer, the EPC contractor, the local authorities, in all these parties there were engineers from the Twente University or from BTG BTL. So it was an innovation network that spoke the same language and had the same values and wanted to realize the same objectives. Next here, please. So what did we do in our book? We did an analysis of 5 industrial successful PI innovations. It was BTG BTL, discussed today, Eastman, Maleta, Shell Omega, and in pharmaceuticals. And in all these cases, we show the importance of soft factors. And I also have to include the Sustainable Development Goals as discussed by David. And that's also a part in our book, but we had no time to discuss it today. But all these cases show that soft factors are very important. And it's about interest. It is about multidisciplinary teamwork. And it's about cooperation in innovation networks. And in our view, these soft factors are also decisive in taking hurdles and increasing the speed of implementation of process intensification. Next dia, please. So if we talk about industrial training, and this is a summary, we have to train industrial engineers in the concept design of 5 domain steps. We have to train them in innovation practices, the VIP model, about innovation practices in the company, about innovation ecosystems. We have to train them, and we discuss that in our book, in innovation stages and the Gates method. We have to train them in industrial cases, showing how engineers succeeded in realizing a breakthrough in PI innovation. And we have in all type of workshops, we have to discuss different types of cases. Next sheet, please. And I think all things you can find in this book, and I hope that when you read the book, you will enjoy it. At least, yeah, partly we had a different background, but we enjoyed it very much to write this book, and I hope that you enjoy it to read it. Thank you very much.
Thank you, Maarten and Jan, for this very interesting presentation. If somebody from the audience has any questions, then please post this in the chat or in the Q&A. I see that Silvia Polverini has a question. Could you mention who are the companies that allocate economical resources in the next 10 years to build up the PI integration in their industries? That's a very specific question. So I don't know, Maarten or Jan, whether you have any answer to this.
I cannot give the complete answer. I only have a very limited knowledge of companies that have applied and are applying process intensification. The largest implementations of process intensification you find, funnily enough, in the oil refineries. So Shell and Exxon, they have built more than 200 reactive distillations. You also find them in the mining industry, where they have used more than 1,500 reverse flow combustors for producing sulfuric acid. I think probably very likely you'll also find them in the specialty chemicals like Arkema, Eastman Chemicals, companies similar like, oh, BASF. Oh, how could I forget BASF? BASF alone has 57 reactive distillations, and I'm pretty sure, although they don't report, that they have many more intensified processes, because they cover the whole field of fine chemicals, specialty chemicals, bulk chemicals, and oil refining. And I'm pretty sure they apply process intensification everywhere. And it makes sense, because you have less capital, you need less capital investment, the energy is lower, the reliability of process intensification is also much higher in general than other processes, because it has less rotating equipment. Rotating equipment is 30% of the reason that processes break down. So they're more reliable as well. Is that, hopefully that's some answer.
I think that answers the question very well, Jan. I'm looking in the chat or in the Q&A. I don't see any questions for the moment. I have a question for Maarten. I thought it was very interesting that you said that we have to go for a multidisciplinary teamwork approach. So besides R&D people, you should include marketing and sales and operations people. Now I'm wondering, as often being in the co-organization of the IPIC conference, for example, does it make sense to try to also accommodate or invite people from the marketing and sales or from the operations into such communities where obviously it's mostly about, let's say, technologies that are still not yet implemented, but that are interesting to be further investigated and developed to full implementation.
Tom, thank you very much for this quite interesting question. Let me tell a small story about the Philips Corporation. In the past, there were these three disciplines: manufacturing, research and development, and marketing and sales were really split up, and there was no integration. And the result was that Philips was rather slow in innovation. And the reason was that all decisions had to be taken at the top. Further, you have to realize that by nature, operations or manufacturing is very conservative because they want a steady process. They don't want any change, to be honest. So if you want to have people with an OPS background to think about OPS, to see also the big advantages, also from a sustainable a development goal point of view and sustainability, then first you have to invite them and to show them what process intensification is about. Second, you have to ask them, if you want to intensify your process, what is important for you? And to be honest, the language of manufacturing managers is different from that of people in R&D. And especially manufacturing managers totally focus on process control. And that was Jan was arguing. He said, if you really design a process from the perspective of PI, then the possibility of process control will increase. And that is what manufacturing wants. So this is an example about manufacturing. I did R&D and manufacturing and not that much marketing and sales, but the same type of stories you can tell about marketing and sales. So I think these people also has to be at this type of conferences.
Okay, thank you very much. I think there's one last question that we will raise here. It's a question from David Bogle, which nicely builds on what you just said. And this extends into the general public. So how do you reconcile conflicting values between engineers and the general public where it occurs? For example, fear of novelty, fear of innovation, different views on sustainability, drive for greater automation, as you said, but also fears about this in the general public, so beyond the company itself.
Yeah, thank you very much. That's also, I like this question very much. I think there's only one answer, and that is the answer about dialogues. And also we have to realize that with PI, we can solve very important societal problems. I will give an example. In the Netherlands, there was chlorine was produced in one factory. By train, it was transported all over the Netherlands. As we know, chlorine is very dangerous. So there were a lot of discussions in the Netherlands, is that allowed? And after a lot of research, they found a process, intensified process, so that it could be manufactured in on the local spot. So that is one example. And I think people are afraid for the chemical industry. I understand that because these operations are so massive. So you will become anxious from it. So the industry has to explain what they are doing and have to start dialogues. And for engineers, I think ethical dilemmas are challenging because when we have an engineering problem, we never can choose one side. We have to balance them. And the same holds for values. You can never say, okay, I only stick on safety and profit is not important, or I only stick on sustainability and customers are not important. You have to do justice to both parts of the dilemma. And that is an engineering a challenge. And engineering liked it because it is a puzzle.
Thank you very much, Maarten, for the answer. And that brings us, strangely enough, perfectly to the next presentation by Wim Dermaut, because he will be talking about bromine and the toxicity and the problems of having bromine in a current process and trying to change that with flow technology. So I will give the floor to Wim Dermaut from Agfa Gevaert. As I said in my introduction, Agfa and Wim's team was the winner of the PI Award for Industrial Innovation in 2019. What I forgot to mention in the introduction is that there will be a new call for both awards, both the Industrial Innovation Award and the PI Excellence Award for Best PhD in 2021. So keep an eye on the EFCE website and newsletter where you will all read about this. So Wim, I give you the floor to hear about the implementation of PI in Agfa Gevaert. You might still be muted.
You're right, I was still muted. Thank you very much for this kind introduction. If everything goes right, you should see my screen now.
Yes.
Okay, perfect. As Tom has already mentioned, this is a presentation which I have already given last year at the conference in Leuven, which represents the case study which we introduced for the Process Intensification Award from the EFCE. So it will be a repetition of that presentation. It's a case study which has also been presented at other conferences. So for some of you, it might look familiar. I apologize for that up front. For the others, I think it is a nice example of how, in this case, a relatively easy process could make a big difference with regards to process safety, and in this case, using process intensification by means of flow technology. So we will take a look at a chemical process which we are running in our company, which was originally run as a batch process where we had to use liquid bromine. So we will discuss a little bit the safety issues which are associated with that. Then we will have a look at the development of the flow process where we were able to remove the need for that liquid bromine in the process altogether. And then since I am a chemist, so you will see there will even be chemical formulas in it, which might come to a shock, as a shock to some of you. But I promise I will try to make it up because I will have some engineering stuff as well with the characterization of the plug flow behavior in our flow reactor. And finally, I will share you some pictures and thoughts on our pilot installation. So let's first have a look at the batch process. So here on the right, you see a typical molecule, which is interesting for Agfa. We use it as a photo initiator in a printing plate. It's not a commercially available product, so we have to make it by ourselves. It's a multi-step chemical process, but the last step involves the bromination. So you can see here on the left, we have the methyl group in the starting molecule, and we have to introduce 3 bromine atoms here on the right in our final desired product. The classical way to do so is to perform the bromination by using sodium hypobromite. Hypobromite is a very strong brominating agent. It's also an oxidizing agent, and it can be very efficient. This process in itself is close to quantitative. It has perfect yield. It has very high purity of the end product. So all in all, chemically spoken, it is a nice process. There is an issue, however, because we have to use this sodium hypobromite, and that is a problem. Hypobromite in itself is not stable, so you really have to generate it on the spot, otherwise it will decompose before you have been able to use it. And a common way of producing sodium hypobromite is by the addition of liquid bromine to a cold caustic, so that means sodium hydroxide or potassium hydroxide in water solution. So you just add the liquid bromine to the potassium hydroxide, and you will have a nice reaction. It's also quantitative, no side reactions. So all in all, it's again, chemically spoken, the generation of the hypobromite in itself is a very neat process. But the main issue is we have to use liquid bromine to do so. So in our current batch, in our original batch process, what we did was in the first reactor, we added the liquid bromine to the cold potassium hydroxide in water, and then that solution was dosed to a second reactor where we had our starting material in toluene. We had a phase transfer catalyst because we have a water toluene mixture which is non-miscible, and then we add the liquid. We add the solution of the potassium the sodium hypobromite, sorry, the potassium hypobromite, excuse me, to this mixture, and then we have a nice reaction. So we need to use two different reactors because we have to take care of the thermal stability of the hypobromite. You can see this here in the next slide. You can see that we followed the concentration of the sodium hypobromite solution over time. And at room temperature, you see here the red curve, and you see that in 24 hours, it decreases from a concentration of about 16% to less than 10%. So this is an issue. If you keep it cold at 0 degrees, you see that the degradation slows down considerably. But even if you keep the mixture at 0 degrees, you see that, okay, this is here in the time is expressed in hours. That means that if you make a fresh solution, you will have to make sure that you use this solution in a time frame of, let's say, about 6 hours. That's feasible to do so if you really tune your processes next to each other, but it makes long-term storage of the product impossible, as you can see. So the traditional way of generating the hypobromite, as mentioned, is just the addition of liquid bromine to cold caustic solution at 0 degrees with a limited stability, and we need to process it at within a couple of hours. Again, this is challenging but not impossible in a chemical installation. We have a large multi-purpose batch installation with several reactors also next to each other and the possibility to transfer liquids between the reactors. So it is feasible, but it's not very practical. The main issue, as I have already mentioned, is the fact that we need to handle liquid bromine. Liquid bromine is quite a nasty chemical, and to be honest, it's about the nastiest chemical we are using in our factory. Why is that? Because it's very toxic by inhalation. It has a TLV value of 0.1 ppm, which is very, very, very low. So that means that everybody working with liquid bromine really needs to have full protection, like you can see here in the picture to the right. You need a full face mask, you need chemical suits and all that kind of stuff. Moreover, it is highly volatile. It has a boiling point of only 59 degrees, and it really gives off this, well, it gives nice pictures, but it's not nice to work with. It really gives this very toxic orange fumes, which can be very dangerous. Moreover, bromine in itself is also very corrosive, both to skin and to metals. So that means that you really have to be careful in spilling, and you really have to be careful that that you don't have any leaks, and you really have to take care of the material compatibility of your entire installation. It's a heavy liquid, the vapor is heavier than air, so it's really something, if not really necessary, you don't want to work with it. An extra problem in our case is the availability of liquid bromine. You can buy it in these bottles of 1 liter from Akros or Aldrich or the like quite easily, but if you want to use it at larger quantities, you immediately have to take the step to 400 liters, which is about 1 ton containers, which look a little bit like this. And if you want to order containers like this, the supplier will perform an audit of your site to make sure that you can work with it safely. So to be honest, to work with liquid bromine on a larger scale, it needs a lot of extra attention in your plant, and it's very difficult to really do so in a safe manner. So all in all, we had a process which was running relatively nicely at a 400 liter scale in production, but with some major issues. As mentioned, the handling of the bromine and the availability of the bromine is probably the largest issue. Also from a costs perspective, there was an issue because in our facility, we are limited to 400 liter scale when we work with this type of highly toxic components. We have at 400 liter scale, we have the possibility to use reactors which are contained, where we have these which are located inside walk-in fume hoods, and with only 1 or 2 reactors in that area, which can be kept completely closed. But the maximum size of the reactor there is 400 liters. So that means that it makes it a relatively expensive process. If we need more of this product, it will become quite an expensive thing because we cannot scale it up to larger scales. As mentioned, stability of the hypobromide, of course, is a main issue. We have to control the exothermicity of the process. And for other chemical reasons, the dosing of the hypobromide needs to be done relatively quickly in 90 minutes, and that can sometimes be a little bit tricky as well. Okay, so this led us to some thoughts, and quite literally during a coffee break, somebody made a remark, well, why don't we make our bromine in flow if it is so dangerous to work with it? And that set us, made us think about the process in a whole, and we did some literature search, and that revealed that hypobromite can be generated directly from bleach and sodium bromide. So bleach is simply hypochlorite. It's household bleach, but then for industrial use, it's with a higher concentration. And sodium bromide is just the bromide equivalent of simple salt, which is sodium chloride. So if you mix bleach and sodium bromide, you will have an exchange of the chloride from the bleach with the bromide from the sodium bromide, and you will generate the hypobromite directly. This was new to us, and it's very strange because when we started looking into literature, we found publications in the Journal of the American Chemical Society dating back to 1948 already explaining this reaction, and moreover, it is a widely used process in the water treatment, where hypobromite is also used for the disinfection of water. So strangely enough, in one industry, this process is very well known, and in another industry, in this case, the fine chemical and organic synthesis domain, this is not so very well known, because if you look up reactions where you use hypobromite to perform a bromination reaction in the current literature, you will still find quite often in, for instance, the Journal of Organic Chemistry, that they have a process description where you first generate a hypobromite by adding liquid bromine to caustic. So very strange that even 50 or 70 years later, it is not commonly known in the organic chemistry field. So this was, of course, very interesting to us, because that would mean that we might have a possibility to generate our hypobromite without the need of this liquid bromine. But of course, the stability issue remains. The hypobromite solution will not be stable. So if we make it in flow, we will have to use it directly. But since we can probably make it in flow, that should not be too much of an issue, because you can just generate the amount of hypobromite you need on the spot. So we did a first lab test with just lab scale equipment. Here on the right, you can see this is our lab scale flow reactor, and this is a lab scale batch reactor. So what we did was we just pumped 2 streams, one with concentrated bleach and one with a concentrated aqueous sodium bromide solution. We pumped them through a coil reactor with a certain residence time. We just chose arbitrarily 20 minutes residence time to give sufficient time for the reaction to take place. And we know that at room temperature, the solution will be stable for at least 20 minutes. So that should not be too much of an issue. So we generate the sodium hypobromite solution inside the coil reactor here. And the outlet of the coil reactor is then immediately attached to the batch reactor, where we have the toluene solution of our starting material sitting, and the bromination reaction can take place immediately. This was just a first a first shot at a 100 milliliter scale, and the first result was already very promising. As you can see, we had 80% conversion, only 7% of a dimeric impurity, and the target compound matched with the reference according to HPLC. So as a first shot, we were extremely satisfied with that, and then obviously we went further on optimizing this process. We did find out that the residence time inside the coil reactor is quite important. Here you see an actual HPLC trace. This is the kind of HPLC traces which makes chemists happy, because this is the starting material. You can just see a little bump here. This is the final product we want, very nicely. And this is just toluene from the solvent. And you can see there's basically nothing else present in this chromatogram. So we have a very nice process, which a very clean product. With high yield and high conversion. So that looks very promising. However, we have to be careful, because in this case we used a residence time of 20 minutes to allow for the reaction between the hypochlorite and the sodium bromide. If we only have a 2-minute residence time, you can see that the picture looks quite differently. So here again you see the starting material, which is a little bit larger, but that's not the main point I want to make here. Here you can see that when we look at the position of our final product, so the brominated process, you see that we can distinguish 3 peaks. And this is quite easily, this can be explained quite easily. These 3 peaks, they correspond to the tribromo, the dibromo monochloro, or the monobromo dichloro. So if you have insufficient reaction time for all the bleach to react away and to be converted into the hypobromide, you will have chlorination instead of bromination, and that is something which we don't want. So therefore, it is important that we have sufficient residence time to make sure that we have no residual hypochlorite left, because that will lead to the chlorinated product. And that brings us to the next point, the characterization of the flow reactor, because we do know that the residence time inside the reactor is critical, because if the residence time is too short, we will have unreacted hypochlorite. But as you all know, if you pump a solution through a plug flow reactor, you will have deviation from the ideal plug flow behavior. And that means that that deviation will lead to part of the reaction mixture which will have a shorter than expected residence time inside the reactor. And that, again, may then lead to chlorination instead of bromination. So therefore, we wanted to know quite exactly what the residence time and distribution profile of our reactor looked like. Residence time distributions are fairly well known and well described in literature for small channels, but not so much for the larger diameters. This is a very interesting article which I would recommend all of you to have a look at. Characterization of milli and microflow reactors, mixing efficiency and residence time distribution. It was published in the Organic Process Research and Development Journal from ACS. It is from the group in Leuven Diepenbeek, and there they describe what the influence of a varying diameter at a millimeter scale is on the residence time distribution. You can see the result here. You will see that here we have the normalized distribution. So in case you have ideal plug flow, you will have a very, very narrow peak centered around this 1 theta here in the middle. So you can see that with the experiments they performed, you can see that at the 0.4 millimeter internal diameter, you had a narrow peak which was centered around 1, which was quite close to the plug flow model. When we then further increase the diameter, you will see that the peak gets broader and broader. And when you go to 4.8 millimeter in diameters, that's about half a centimeter, you see that we really shift from the dispersion model to the convection model. And you can see that part or even a fairly large part of your reaction mixture will see a residence time which is only a little bit over half of the expected residence time. So if you just calculate the residence time from the volume of your reactor and the flow speed that you're using, you will be mistaken, and that in this case you might have you might have part of your reaction mixture which has had only half of the expected reaction time, which in our case could be an issue. So therefore, we wanted to make sure that in our specific setup, where we used a coiled reactor with diameter of the tube between 10 and 13 millimeter, we really wanted to make sure that we had a sufficient narrow residence time distribution. So therefore, we did some tests where we used the salt plug method to see what the residence time distribution was in our specific case. So again, we wanted to have experimental proof that the residence time distribution is acceptable for both the 10 and the 13 millimeter internal diameters, and we also included large diameters to see how far we could go. A wide range of residence time experiments was set up as input for CFD modeling, also at the University of Leuven, where we varied the length of the reactor, the coiling diameter of the reactor, and the flow speed of our mixture. As mentioned, it was a collaboration with the University of Leuven. Professor Kuhn and Professor Thomassen collaborated in this. And so we experimented with tube diameters of 10, 13, and 25 millimeters. We used flow speeds corresponding to Reynolds numbers of 700, 960, and 1280. And we used different coiling diameters and straight tube. And what you can see here in the graph underneath, this is a very nice example. Here you could see that in our current setup, 100 meter length and the flow speed needed for a residence time of about 20 minutes, you could see that for 10 millimeters and 13 millimeters, we had a quite acceptable residence time distribution, nicely centered around 1. It was a little bit early elution, but nothing too dramatic. But if you make the switch, if we switched from 13 to 25 millimeter, there you could see quite a dramatic difference. And you could see that the early elution here was much more significant than in the two other cases. So this led us to the conclusion that using a 13 millimeter diameter coil would be acceptable for our process. Okay, so let's have a final look at what it looks like in practice then. So when running the process first at 400 and then later on also at 1000 liter reactors for the bromination, we do need two flows, the sodium bromide in water and the sodium hypochlorite, bleach, which is also a concentrated solution in water. We use an excess of sodium bromide, and that means that pulsation of the pump is acceptable because we don't have a very, very strict stoichiometric control which is needed. So we can live with some pulsation. Because we use aqueous solutions for both streams, we can use magnetic flow meters, which are Teflon lined, certainly for the bleach that is needed because it is highly corrosive, and they work very well to have a nice flow measurement on these flows. And then we have a feedback control loop, so the signal from the flow measurement will steer the pump and will control the flow from the pump. For the pumps, we did use quite simple peristaltic pumps, which was very nice because peristaltic pumps are a cheap solution, but they have several big advantages. A big advantage is that you don't have any metal parts in it if you don't want it, so you can have it perfectly Teflon lined or with other plastic materials, which is ideal for our hypochlorite solution, because otherwise we would have serious issue with corrosion. They're also very cheap, and they have a very wide span of flows which can be used with one set of pumps. So therefore, for us, it was an ideal case. Disadvantage of this type of pumps is that they give some pulsation, but as already mentioned, because of the chemistry we use, this is not really relevant for us. So we were fine with these pumps. And then both pumps are controlled from one controller box, meaning that if something goes wrong, that we can shut down the two pumps immediately, and that we have a perfect control over the flow of the two streams together. So when looking at the reactor, this is our home built coil reactor. It looks like just some cardboard drums with a garden hose attached to it, and basically that's perfectly what it is. You can see it's a dead cheap solution, but it works perfectly because in this case it's just some reinforced PVC tubing that you would use in the lab for connecting water hoses or something like that. It works perfectly. It's also transparent, so So that makes it easy to see if we have any air bubbles left inside our reactor. It's all sloping upwards so that you have a nice flow distribution. The hypochlorite solution in itself is yellow at the start and turns more orange to the end. So you can see it visually as well that the reaction is taking place. And it works very nicely. And again, yeah, it's dead cheap and it's very robust. It works as it should. To enhance mixing, of course, because you can imagine this is obviously laminar flow profile inside your reactor. We just threw in 100 of these small disposable static mixer elements. They just cost €1 each. So we just threw 100 in the first meter. That will be certainly sufficient. You could probably do with less, but calculating how much we would need would be more expensive than just throwing in 100 pieces of them. We have run quite a lot of pilot productions so far. We have saved already more than over a ton of liquid bromine, which we didn't have to buy, which we didn't have to store, and which we didn't have to use. So the safety gain which we had there was quite nice. So that brings me to the conclusions of this presentation. So we were able to develop a flow process to produce aqueous hypobromite solution in flow where we didn't need any liquid bromine at all, only bleach and sodium bromide. This is, of course, a huge benefit with regard to safety. And it was also very practical because it was just a plain drop-in for the bromine process, because we also use the standard hypobromite solution exactly the same as we produced in our batch process. So there were no issues with reclassification of the process and so on. We were able to have a proof of concept with cheap non-ATEX equipment, and we are now in the final phase of building together an ATEX approved skid to do the same in our larger reactors. Proof of concept for scale up to 1,000 liter has already been demonstrated, and all this results in a cost reduction of 30%, which is just purely due to the larger scale which we can operate at. And final take-home message, I think, is also when exploring new technologies with a limited budget, aim for the low-hanging fruit first. So in this case, it was technologically spoken a very easy solution, but with a very big impact on process safety and also on cost for this process. So it was really a no-brainer. So that leads me also only to thank the entire Brominator team, Bart Capins, Peter Kempenaars, and Gert Engelen from Agfa, both in Mortsel and in Hultje. Also the analytical department. We have also, part of these investigations have been funded through projects from Vlaio, Agentschap Innoveren en Ondernemen in Flanders, and Catalysti through the Atom project, which is also gratefully acknowledged. So that was it. I hope this was of a little bit of interest to you, and I'm happy to take any questions.
Okay, thank you very much, Wim, for this very interesting presentation. We indeed have a question from Christoph Held, who is telling us very nice. One question regarding the two-liquid phase system: is handling of liquid bromine dangerous, in the sense that, for example, heavy stirring to increase the mass transfer would be prohibiting? That's his question. And then a suggestion or a thought is one way out might be the addition of a co-solvent that acts as a phase transfer agent, such as an alcohol, producing a homogeneous liquid phase made of water, alcohol, and toluene.
Okay, those are very nice suggestions. The first part of the question, if I got it right, adding the liquid bromine to the cold caustic solution with regard to mass transfer is absolutely not an issue because it reacts immediately with the cold caustic. And the final mixture, the final hypobromite solution is a nice homogeneous solution. And when you just do it in a stirred tank reactor, we didn't have any issues at all with mass transfer in that phase. The second part of the question is also very interesting. It's a good suggestion, and I think indeed it would certainly be possible to go to other to go to other solvent systems where you can keep the mixture homogeneous. But in our case, it's easier to do it in a heterogeneous system, because afterwards we simply have to do extractions where our final product is soluble in the toluene phase, and you have quite a large amount of salts which are water soluble, which need to be removed from the product. So what we simply do is we just do extractions with water, and we just keep the toluene phase, and then we isolate the final product from the toluene phase. So in this case, turning it into a single phase system would be rather a disadvantage rather than an advantage.
All right, thank you. If there's any further questions, you can still post them in the chat or the Q&A. Yes, Peter Henry has a question. What are the biggest barriers in your experience to process intensification and its implementation on a process plant that is already operational, as opposed to proposing intensified processes at the design phase?
Okay, it's a very relevant question. I am a chemist by myself, and I have been heavily involved in the introduction of flow chemistry here at the company. And you see that indeed, sometimes it is a little bit difficult to convince people to start doing this type of things. The advantage of this process was that it is the first case where we really go to our production plant with a flow process, and in this case, it is the advantage is mainly safety related. And the good thing is that if you go to a production installation, and if you can really demonstrate a clear increase in safety, that makes it sometimes easier to convince people. The good thing is you cannot calculate down on safety. If it's a cost issue, then quite often you have the risk indeed that people who are a little bit more conservative with this regard, that they will start to calculate and to see, yeah, all these investments which we need and all the changes which we need, if it's only for this one single process, you really need a very, very strong economical case to justify the research, to justify the investment in CapEx and so on. When it is safety related, that often makes things quite a bit easier because it's difficult to say safety. We don't believe in safety. We don't do that. So if you have a good case and if it's safety related, sometimes that makes things easier. And here again, we have been lucky that in this case it was an extremely easy case, because the only thing we need is some good pumps with feedback control. The process is at room temperature, is at atmospheric pressure, so that makes the constraints for the entire installation relatively easy, and it's quite easy to introduce this. So I think if you really want to go for this type of innovation, if you really want to go for this type of process innovation, again, try to aim for the low-hanging fruit first and make sure that you have a first proven case with relatively easy technology, and then try to step up to the more complicated ones if possible.
This is a perfect concluding comment, I would say, for the entire session. Thank you very much, Wim, for your presentation. I think this ends the session. I'd like to thank once again all the speakers, David, Jan, Maarten, and Wim. I'd also like to thank the organization by the EFCE, Martin, David, and Ines. Thank you very much. I'm convinced that the whole series was a success, so this is certainly something we can do again. And I'd also like to thank the audience for being present. And as we said before, the recordings of this session will be made available, I guess, through the EFCE website. Martin, Ines, is there anything else that you still want to mention?
That's okay for me. Thank you for attending this webinar. I think it was very good. Another very good webinar. Yeah.
Okay, so then this is the end of this session. Thank you very much, and hope to see you again in one of the next webinars. Bye-bye.
Bye-bye.